Let's continue studying complex numbers. We are considering the division now, and we have received the result for dividing two complex numbers in the standard form, real part plus imaginary part multiplied by I. Let's try a different method, because this method was a nuisance. We had to solve a system of linear equations, and it was pretty long. I will do the following. Keeping in mind formula number 10, or the preceding result, yes, z multiplied by z conjugate turns out to be a real number. And that's what we need here for the denominator of the fraction. So I will do the following. I will write 2 minus I divided by 3 plus 2I equals. I will divide and multiply this numerator and denominator by the same number, by the conjugate of the denominator. So it will be 3 minus 2I. How to make the complex conjugate? You just put minus ahead of every I that you meet in the number. And it will be 3 minus 2I here as well. So it will be multiplied through 6 minus 4I minus 3I and minus I multiplied by 2, so it will be 2I squared. I will write it like this, plus 2I squared. Divided. What will be here? You can multiply through honestly, or you can just remember this result. So it will be 3 squared plus 2 squared. So it will be 6 minus 2, it will be 4. Negative 4 and negative 3 will be negative 7, negative 7I, divided by 13. Or, to separate real part and imaginary part, divide each term in the numerator by the denominator, will be 4 13ths minus 7 13ths I. We obtain the same result much faster. In general, whenever we have to divide one complex number by another, a plus bi divided by c plus di, we know how to proceed. We will multiply and divide this fraction by the conjugate to the denominator. So it will be a plus bi multiplied by c minus di divided by c plus di, c minus di. So it will be ac, and here will be bd with minus and another minus from I squared. So plus bd, right? When we multiply these two terms, what we will have? bi di with minus ahead of it, yes? So it will be minus bd I squared, and I squared will give another minus. So ac plus bd plus I multiplied by bc minus ad divided by c squared plus d squared. Or you can just continue this writing. I will separate real part and imaginary part. It will be ac plus bd divided by c squared plus d squared plus I multiplied by bc minus ad divided by c squared plus d squared. This way we have an easy expression for the division. Of course, you don't have to memorize it. Whenever you have to perform the division, just multiply by and divide by the conjugate to the denominator. And you will get the right result. Some properties of conjugates and moduli of complex numbers. These properties are pretty evident, and I would advise you to prove all of them, or at least some of them, as an exercise. Maybe you will have to prove them as part of your exam. And so it's a good idea to practice a little bit, and also it helps you to learn. It helps you to learn the new toy. You receive a new toy, complex numbers, right? How to deal with this, how to operate with it. Here is how. You play with it a lot and you're getting used to it. Yeah? What are these properties? What are these properties? For instance, if you multiply two complex numbers, z multiplied by w, the same as with absolute values of real numbers. It is the same as modulus z multiplied by modulus of w. Similarly, if we divide z divided by w, will be norm of z divided by the norm of w. What else? Of course, it will not work for addition, the same as with absolute values, yes? I will make a note that in case when z is real, modulus z is just the absolute value of z, and the meaning of this absolute value is the same. The distance, this meaning is always the same. The distance between z and z. It's actually the norm of your vector. Yes. When you make the correspondence between z belonging to the complex plane, right? And you make one correspondence, your isomorphism. Your isomorphism with vector v that belongs to R2, then of course modulus z can be put in correspondence with the norm of vector v. Modulus is correspondence with the norm or length of the vector. Yes. What about the conjugates? What are properties of conjugates? I want you also to prove some properties. Z multiplied by w conjugate, you can guess, will be z conjugate w conjugate. Z over w conjugate will be the same as z conjugate over w conjugate. It's interesting that these properties also hold, yes? Also, in contrast with the properties of moduli, z plus w conjugate is z conjugate plus w conjugate, which is quite easy to prove. Yes, it's trivial to consider. Sometimes people consider separately multiplication by real numbers. If you have a real number alpha, real number multiplied by z conjugate will be of course the same as alpha multiplied by z conjugate, since alpha conjugate is equal to alpha, right? We can prove some of this. We can prove some of these properties. They are very, very straightforward. I can prove, for instance, the property number 1, which is a faster one. Then you can prove property number 2, and also prove properties for the modulus of complex numbers. So I want to prove that z multiplied by w conjugate equals z conjugate multiplied by w conjugate. So what do you have to do? How do you prove it? You have to consider left hand side and probably reduce it to some expression, and then consider right hand side, reduce to the same expression. Don't start with writing this as if it has been proved already. That's a mistake. And on exam, whoever proves something starting with what is needed to be proved will receive 0 credit for this consideration, for this problem. So don't do it. So how do you prove it? I say, suppose z is some number, x plus iy, w is some number, u plus iv. So z multiplied by w and then taken conjugate. This bracket is kind of superfluous, but I want to emphasize that I take the conjugate to the product. You don't have to write this bracket in this case. Equals x plus iy multiplied by u plus iv, conjugate of the whole this thing, equals x u plus I xv plus I yu plus I squared yv, and it will be xu minus yv plus I xv plus yu. That's the expression for z multiplied by w. Oh, that's a surprise. Pencil doesn't work anymore. Z multiplied by w and then taking the conjugate. Let's consider the next expression. The next expression will be what? Z conjugate, w conjugate. Z conjugate multiplied by w conjugate will be x minus iy, that's Z conjugate, multiplied by u minus iv, that's what's conjugation, yes, we put minus before all i's that you have, and it will be xu minus xi. I'm very sorry, I forgot. I'm very, very sorry. I did not finish this calculation. Why I did not finish this calculation? Because I forgot this symbol of conjugate going over the whole this thing, going above the whole this thing, and so therefore it will be, the conjugate of this number will be what? The first bracket, xu minus yv minus, yes, that's what conjugate tells me. Put minus before I. Minus I xv plus y. Now it is finished. I'm sorry. This error. So be careful. Don't repeat errors. Mine or anybody else's. So let's now try the second expression. Now the second expression. It will be z conjugate multiplied by w conjugate. It will be x minus iy multiplied by u minus I u minus iv. So it will be x u minus I xv minus iy u, and plus, because it's minus times minus, plus I squared yv. So it will be xu minus yv, and I factor out minus I, here is also factor out minus I, and here will be xv plus yu, xv plus yu. This expression is the same, right? We started with this one, we received this one. We started with this one, we received the same expression. So you can write therefore ZW conjugate equals Z conjugate multiplied by W conjugate. The use of these properties, of course, in the following. Whenever you see some complex numbers and operations performed over them, in order to get the conjugate of this expression, just put minus before every I you see in this expression. Right? And you will have the right result. So for instance, if you just want to write the expression for the conjugate, for some number, so for instance number z equals 3 plus 5I squared multiplied by 3 minus I divided by 2 plus 11I. If you want to write the expression for the z conjugate, I don't say calculate in standard form, it's easy, but it's a lot of writing. So we just say z conjugate will be 3 minus 5I, so we put minus before this I, squared, the rest is the same, multiplied by 3 plus I, and divided by 2 minus 11I, minus before this I as well. That's all. These are the properties of the conjugates. Whenever you have to prove something concerning conjugates, moduli, modulus is in singular, in plural, you say moduli, and you write like this. It's Latin, fine things about these Latin words. So when you say, oh, this is pencil which I cancelled already, it emerges again. Whenever you say modulus, you say moduli in plural. It's a singular, it's in plural. I think you've seen some other examples of words of Latin origin. I think we will stop here for a while. We may consider more and more interesting problems with complex numbers, but so far I'm a bit in a rush to introduce all the important notions. Now, we can describe complex numbers, as we saw, as two-dimensional vectors, as Cartesian vectors. Yes? This is called standard form or Cartesian form, whenever we have an expression z equals x plus iy, it's called a standard, or Cartesian form of a complex number. Standard or Cartesian form. Are there any other forms? Of course there are, because you know what may happen in the plane. So this is x or real part z, this is y or imaginary part z. Whenever we have some number z, it's not necessary to write this arrow, but it is convenient, and it is convenient to view operations with complex numbers as operations on vectors. As you will see pretty soon, even multiplication of complex numbers can be seen very clearly geometrically what it means. So this is x and this is y. You can consider these vectors differently. In order to find this terminal point of vector z, it's enough for us to know the distance or modulus of z, or we will denote it r as polar radius. Will be one of our notations. R will be by definition modulus of z, or square root of x squared plus y squared. This will be formula, I think, 1 for today. What else do we need? The angle formed by this vector, theta, I will denote it theta, between some certain direction and this vector. I will denote it theta, and I will say that theta is an angle between z and real part z. Of course, we mean the positive direction, no question about it. All axes have only one direction, positive. How can we find the expression for theta? I can see from this formula that sine theta equals y over modulus z, or y over r, and cosine theta is x over r, as we can see from this triangle, or we can see from the unit circle in case when x and y are negative. So this is formula number 2. We realize that tangent theta is, of course, y over x. This is the formula number 3, and this relations number 2 tell us that theta is determined up to 2 pi, because if we add to theta a complete revolution, or we subtract a complete revolution, we will have the same sine and cosine. So theta is defined up to 2 pi n. So angle, I will call it argument z, it's another name for theta, equals theta plus 2 pi n. This will be formula number 3. Reduces z, the same number z for any n. So we will select one of these angles as the most important one. So theta is general. Theta is called the argument of z, and denoted theta equals arc z, theta equals arc z, and one of these values we will single out for our convenience, will be more important than others. Theta equals argument z, and it's called the principal value of the argument if it is located between pi, it is less or equal pi, and greater than negative pi. This will be formula number 4 for today. This will be formula number 4 for today. For instance, just to show it in a picture. If we if you have number z located here, if this is our number z, well, let's just take w, just to have a different notation. This is the origin, yes? This is the origin. And we have angles associated with this w. We can consider this angle, alpha, and we can consider this angle, beta. Which of them, I can ask a question, which of them, alpha or beta, is the principal argument of W? And now we recall that argument of W must be between pi and negative pi. Which one fits? Of course, then it is beta. Beta is the principal argument of W, since beta is between 0 and negative pi, right? It goes in the negative direction, but it doesn't reach pi. And alpha is greater than pi. Alpha goes passing pi and goes more. So it is beta in this case. The argument is negative. Let's go further. Now we can present our complex numbers in the so-called trigonometric form. This is our next next topic. And this trigonometric form will give us amazing understanding of complex numbers and of geometry, and even of geometry of multiplication of complex numbers. So this will be our next. Complex numbers in trigonometric form. So we have a complex number, z equals a plus ib, and we know from the previous consideration the notions of the modulus and argument. So I will do the following. I will say this will be formula number, I don't remember, let's say 3 for today, doesn't matter really. We can introduce the notion of R equal modulus Z or square root of a squared plus b squared. This will be formula 4. And theta, argument, some argument of z, such that cosine theta is a over r and sine theta is b over r. This will be formula number 5. Now I will rewrite from the number z in a slightly different form. I will say z equals, I will factor out r. I will write r. I factor out r from here and r from here. So what's left? A over r plus I b over r. Oh, what is this? This is a over r is cosine theta, b over r is sine theta. So it will be r cos theta plus I sine theta. This will be formula number 6, and this formula presents number z in trigonometric form. This is trigonometric form of number z. It turns out it is often convenient to see number z in this form. So let's consider some examples of transforming z in this form. So example number 1. Write z in trig form. Z equals 1 minus I. Present in trig form. What shall we do? We have to find the modulus of z, yes? R, or modulus of z, equals square root of 1 squared plus the imaginary part is negative 1 squared. So it will be root of 1 plus 1, root of 2. Right? And I will keep writing here. I can write z equals 1 minus I will copy again. So I factor out root of 2. Factor out root of 2, and it will be 1 over root of 2 minus 1 over root of 2i. So this is actually z in trigonometric form. You can also recall that cosine of pi over 4 is 1 over root 2, and sine of pi over 4 is negative 1 over root 2, and therefore you can write z as root of 2 cosine pi over 4 minus I sine pi over 4. Also you can rewrite this number z. It doesn't give you any advantage, but just to realize what's happening. Z equals root of 2 cosine of negative pi over 4 plus I sine of negative pi over 4. Why did I prefer writing negative pi over 4? Because negative pi over 4 is the principal value of the argument of z. It's located exactly between 0 and negative pi. Yes? So this is the principal value of the argument. Yes? And the trig form must look like this. R cos theta plus I sine theta. It's a different matter that sine of negative theta is negative sine theta because of the properties of sine. But if you want to know the principal argument of the z, it is actually root of 2. Now let's look at a few more interesting things. So you must be able to present z in trigonometric form. In case sometimes you don't have the special values, like here I had pi over 4, and I suggest that you know the trig functions for special values of angles, which are pi over 6, pi over 3, and pi over 4, and you must be able to find sines, cosines, and all the tangents for all the angles related to this, all the angles for which these 3 angles are reference angles, and you must remember their trig functions. And I think I will post on Blackboard some supplementary materials on trigonometry, because I can guess some people do have trouble with trigonometry. But you may also have examples when your angles, the argument of your example number 2, the argument of your complex number is not really a special trig function. An argument is not special angle or related to a special angle. For instance, I want to present in trigonometric form number z equals 1 plus 2i. What will you do with this one? You do the same thing. You calculate r, or modulus z equals square root of 1 squared plus 2 squared, so it will be root of 5. Then you will write z equals root of 5, and it will be 1 over root of 5 plus I 2 over root of 5. Or you can rewrite it as root of 5, and here will be cos theta plus I sine theta as usual, and then you say where theta is, you can just say, if you divide y over x, arc tangent 2. Arc tangent of 2, right? If you divide sine by cosine, you get tangent, will be 2 root 5 or 1 root tangent 2, which is actually argument of z. How do I know this arctangent 2 is located between negative pi and pi? Because I know where is arctangent 2. If I draw the unit circle, this is the tangent axis, this is 1, this is 2. Where is arctangent 2? This angle. This angle is arctangent 2. This is your theta. So I can see this angle is located between negative pi and positive pi. So you can repeat it always. Your angle will not always be arctangent, but it will be always, for this angle, arctangent will be the reference angle. And we will consider more examples about it. So far, please practice operations with complex numbers, prove the identities I ask you to prove, and practice transforming complex numbers in trig form. It is a very important skill. And I will provide you with some problems. I provide you with some materials from a textbook and some handout in which you will have plenty of